In 1915, a young British engineer built an engine so efficient that the War Office refused to believe the results. His prototype consumed less fuel, produced more power, and ran cooler than anything then in service. Officials assumed there must have been an error in the readings. The engineer was Harry Ricardo, and the figures were correct. Britain was deep in the First World War, desperate for reliable engines to power tanks, lorries, and aircraft. Most of them overheated, misfired, and wasted precious fuel. Ricardo's test engine, built in a modest workshop in Sussex, seemed to defy all convention. His discovery, that the real secret of power lay in how fuel and air mixed before ignition, would eventually redefine mechanical engineering. But at the time, few people outside his small team understood what he had done. Harry Ralph Ricardo was born in 1885 in London, into a family that valued invention and science. He studied mechanical sciences at Trinity College, Cambridge, where he quickly developed an obsession with the internal combustion engine. Whilst most students were content to build simple steam experiments, Ricardo spent nights analysing flame fronts, compression ratios, and heat losses. He wanted to know why engines wasted energy, and how to stop it. After graduating in 1908, he began designing experimental petrol engines for motorbikes and cars, focusing on cylinder efficiency and smooth combustion. His early prototypes already produced more power than most commercial designs, but Ricardo cared little for selling machines. What fascinated him was combustion itself, the invisible chemistry inside a metal cylinder that turned vapour into motion. When war broke out in 1914, Britain's new weapon, the tank, was in trouble. The earliest prototypes were fitted with heavy, unreliable engines borrowed from farm tractors. They overheated, stalled in mud, and sometimes caught fire after only a few hours of operation. The army turned to Ricardo's fledgling company, Ricardo Engineering, for help. He accepted, moved to Shoreham by sea, and began what would become one of the most influential engineering studies of the war. Within months, Ricardo's small workshop had built an entirely new power unit. Using careful analysis of heat transfer, improved air-fuel mixing, and a redesigned cooling system, his engine could run for hours under load without overheating. When tested on the Mark V tank, it performed flawlessly. Soldiers who had spent months wrestling with temperamental machines now drove vehicles that could finally keep moving under fire. The War Office, once sceptical, suddenly realised what Ricardo had achieved. His design didn't just improve performance, it transformed the tank from a mechanical liability into a dependable weapon. For the first time, massed armour could move with confidence across the Western Front. Unlike many inventors, Ricardo wasn't guided by intuition or luck. He trusted data. He built some of Britain's first scientific engine test stands, recording pressure waves, temperatures, and flame speeds with meticulous precision. His notebooks were filled with calculations linking fuel chemistry to engine geometry mathematics that most factories of the era never considered. Colleagues said he treated every engine like a laboratory experiment rather than a product. That discipline gave him insight into a problem that plagued every internal combustion engine of the early 20th century: detonation or knocking. When fuel ignited too soon, it wasted power and could destroy an engine in seconds. Ricardo began studying how compression and fuel quality interacted, setting the groundwork for what we now call the octane rating. His research proved that by controlling the burn rate of fuel, engineers could safely extract far more power from the same engine size. By the end of the war, Ricardo's name had quietly spread through the engineering world. His redesigned tank engine became the pattern for future British armoured vehicles. More importantly, his understanding of combustion efficiency began influencing aircraft manufacturers and car companies alike. Rolls-Royce, Vauxhall, and Bentley all sought his advice during the 1920s. He didn't chase contracts or publicity. Instead, he focused on refining his scientific methods, publishing technical papers that read more like physics than mechanics. Each paragraph replaced superstition with measurable cause and effect. In a field once dominated by trial and error, Ricardo brought order and mathematics. In 1919, he formalised his company as Ricardo Company Limited, building a dedicated research facility at Shoreham. There, he continued to explore how fuels behaved under pressure and heat. Every result, every diagram, every misfire was logged and studied. His laboratory became a quiet powerhouse of British innovation, producing data that would soon guide engine design across the world. What began as an urgent wartime solution was evolving into a lifetime of discovery. The problems of knocking, efficiency and power output were not just military concerns. They were the future of transport itself. Ricardo understood that as engines became faster and smaller, precision in combustion would decide progress. He had turned the act of burning fuel into a science, and soon that science would make Britain's engines, on land, sea and air, stronger than ever before. After the First World War, Harry Ricardo's reputation as one of Britain's leading combustion specialists was firmly established. The army had seen what his tank engines could do, and industry began to realise that the same scientific approach could transform civilian power as well. His small workshop at Shoreham was now a fully equipped research laboratory, a place where engines were no longer built by instinct but by mathematics. The war had taught Ricardo one lesson above all, that reliability mattered more than raw power. The tanks of 1916 had proved that an engine which worked in a laboratory was useless if it failed in battle. So, in the years that followed, he devoted himself to understanding the behaviour of combustion under every possible condition: heat, pressure, altitude, and fuel quality. His methods were obsessive but revolutionary. Where other engineers guessed, Ricardo measured. He began by dissecting the causes of detonation. The sudden knock that destroyed pistons wasn't random, as most believed. It was the result of unstable fuel igniting unevenly before the spark. Ricardo designed transparent cylinders and used optical instruments to observe the flame itself. He discovered that the shape of the combustion chamber, the turbulence of the air-fuel mixture, and the volatility of the petrol all determined how smoothly an engine ran. It was the kind of work that no car manufacturer had the patience or precision to carry out, but Ricardo did. By the early 1920s, major British firms were sending him engines to test. Rolls-Royce sought his help on early aero engine projects, while Vauxhall and Crossley consulted him for improving commercial vehicles. His research on octane numbers, a measure of how resistant a fuel is to detonation, became a benchmark for the petrol industry. The higher the octane, the more compression an engine could safely withstand, and the more power it could generate. That simple relationship changed the course of engine design for the rest of the century. At the same time, Ricardo began investigating diesel engines. They were still crude and noisy machines, but he saw potential in their thermal efficiency. He worked on combustion chamber shapes that made diesel burn evenly, reducing smoke and increasing power. These experiments laid the foundation for the modern high-speed diesel engine, which would soon dominate commercial transport. By the mid-1920s, his company, Ricardo and Company Engineers, had grown into one of the most respected independent research organisations in Britain. Governments, car makers, and even aircraft manufacturers sent designs to Shoreham for testing. Every experiment was logged, every anomaly explained. Ricardo believed that engineering was as much about understanding failure as success. If a piston cracked or a valve burned out, he would study it under a microscope until he knew exactly why. The interwar years also saw him advising the Air Ministry, where his knowledge of fuel behaviour proved vital. Aircraft engines of the time suffered from detonation at high altitudes, where the air was thinner and cooling less effective. Ricardo's studies led to the development of special high-octane fuels and improved combustion chamber designs, allowing pilots to climb higher and fly faster without destroying their engines. This quiet work in laboratories and hangars would later prove decisive when Britain faced its greatest test. Though he was now one of the most respected engineers in the country, Ricardo avoided the spotlight. He disliked self-promotion and preferred the company of his instruments and apprentices to banquets or awards. His laboratory was modest but disciplined, every tool in its place, every test documented. Visitors remarked on how calm the building felt, as if the noise of industry had been replaced by the precision of science. By the 1930s, Ricardo's findings were shaping not only military design, but also civil progress. His papers on heat efficiency, fuel injection, and turbulence were circulated across Europe and America. He worked with Shell and BP to develop better refining techniques, ensuring that Britain's petrol supply was cleaner and more stable. When the Royal Navy began fitting diesel engines in submarines, it was Ricardo's combustion research that made them reliable. He was now far more than an engineer. He was a teacher of principles. His philosophy was simple. Every improvement begins with measurement. Guesswork, he said, is the enemy of progress. That belief echoed through every project that bore his name. As the clouds of war began to gather once again over Europe, Ricardo's work took on a new urgency. The engines of the coming conflict would need to be faster, tougher, and more efficient than ever before. The laboratories at Shoreham buzzed day and night with experiments. New fuels, new pistons, new methods of cooling. Ricardo's team, though small, produced results that influenced aircraft and tank production across the nation. He didn't see himself as part of the war machine, but as part of its survival. He often said that good engineering saves lives because reliability prevents failure. In 1939, when Britain once again found itself at war, his ideas, quietly developed over decades, became the difference between victory and defeat. By then, the Ministry of Aircraft Production and the Royal Air Force relied on Ricardo's research on combustion control and high-octane fuel. Every Spitfire and Hurricane that took to the skies did so with engines fine-tuned by principles he had discovered years earlier in his Sussex lab. Harry Ricardo's war would not be fought in trenches or cockpits, but in test cells filled with smoke, pressure gauges, and endless data sheets. And it was a war he was uniquely prepared to win. When the Second World War began in 1939, Harry Ricardo was 54 years old, still active, still curious, and still working late in his Shoreham laboratory most nights. His research from the interwar years had already shaped Britain's engines, but now his knowledge would help decide the survival of a nation. Britain's air defence, mobility and logistics all depended on fuel efficiency and engine reliability, both fields in which Ricardo had become the quiet authority. At the outbreak of war, the Ministry of Aircraft Production turned to him once again. Aircraft engines were being pushed beyond their safe limits, especially in high-altitude combat. When engines detonated, they lost power or failed completely, often costing pilots their lives. Ricardo's earlier work on detonation, compression ratios, and fuel quality had already proved that the answer lay not in more power, but in better combustion control. His research became the backbone of Britain's high-octane fuel strategy. Working alongside Shell and the Air Ministry, Ricardo's team perfected new fuel blends that allowed higher compression without knocking. This meant that fighter engines such as the Rolls-Royce Merlin, used in the Spitfire and Hurricane, could produce more power without damage. Those extra revolutions per minute, gained through chemistry and precision, gave Britain's pilots the vital edge in the skies during the Battle of Britain. The victory was as much a triumph of engineering as of courage. Ricardo's name rarely appeared in wartime newspapers, yet his fingerprints were on nearly every British engine. His firm worked on tank and armoured vehicle engines, marine diesel units for the Royal Navy, and auxiliary generators for field operations. Each design benefited from his methodical approach: measure, test, refine. His laboratory became a national asset, guarded and operated under government supervision, but always under his quiet leadership. He often said that good engineering wins wars before they start. For him, this meant foresight, solving mechanical problems in the workshop long before they could appear in battle. While aircraft engineers worked on speed and firepower, Ricardo focused on endurance, how to make machines run longer, smoother, and with fewer resources. The results of his fuel research extended beyond combat. The same principles improved lorries, ambulances, and even portable generators used by medics in the field. Despite the pressure of wartime secrecy, Ricardo continued to publish technical papers, carefully worded to hide sensitive details while still advancing science. His studies on heat loss, turbulence, and pressure propagation inside cylinders became foundational material for the next generation of engineers. Universities and companies worldwide relied on his data, even if they never knew its military importance. One of his most significant wartime achievements was the refinement of diesel engines for naval service. Submarines and escort ships required engines that could run for long periods at variable loads without overheating. Ricardo's expertise in airflow and cooling made those engines more efficient and reliable. The improvements weren't glamorous, but they saved countless lives at sea. In the final years of the war, Ricardo began experimenting with gas turbines, an idea that connected directly back to the combustion principles he had spent decades studying. He saw in them the potential for the next great leap in power generation. Though his own company focused mainly on piston engines, he maintained close contact with the teams developing the first jet engines. He admired their ambition, but warned that efficiency, not speed, would define the future. As victory approached in 1945, Ricardo's laboratory remained a place of relentless work rather than celebration. His engineers were already analysing post-war requirements, civilian transport, rebuilding industry, and converting military research into peaceful applications. He believed the lessons of war should lead to better technology for ordinary life, quieter engines, cleaner fuels, and machines that wasted nothing. By the end of the conflict, Britain's engine technology was among the most advanced in the world. Much of that progress could be traced back to Ricardo's insistence that every problem had a measurable solution. The octane system he had pioneered decades earlier was now the international standard. His cooling designs were copied across Europe and America, and his theories of turbulence and combustion dynamics would soon influence rocket and jet propulsion. When peace returned, Ricardo was recognised as one of the architects of Britain's wartime engineering strength. Yet he declined honours at first, preferring to return to research. He often said that invention never truly belonged to the inventor, it belonged to the world once proven. What mattered to him was not fame, but function. Harry Ricardo's war had been fought in silence, with equations instead of gunfire, and measurements instead of medals. But when Britain's engines roared, it was his science that made them roar longer, louder, and smarter than anyone else's. When peace returned in 1945, Sir Harry Ricardo was already thinking ahead. Britain needed to rebuild its transport, industry, and energy supply, and his laboratory at Shoreham was ready. Instead of designing weapons, he turned his attention to cleaner fuels and quieter engines that could serve civilian life. Buses, tractors, and industrial generators soon ran on Ricardo-inspired systems that used less fuel and lasted longer. In 1948, he was knighted for his contribution to engineering. He accepted the honour with characteristic modesty, insisting that progress had been a team effort. Those who knew him said the title changed nothing. He still arrived early at the lab, notebook in hand, asking young apprentices what they were measuring that morning. Through the 1950s and 1960s, the world around him shifted from pistons to turbines, and from mechanical linkages to electronic control. Yet Ricardo's principles endured. His book, The High-Speed Internal Combustion Engine, remained the standard reference for engineers everywhere, not because it offered formulas, but because it taught how to think, observe, test, quantify, refine. He encouraged collaboration between universities and industry, believing that research meant little if it stayed behind closed doors. Long before environmentalism became a concern, He warned that the engineer's duty was to make machines cleaner and more efficient, that waste, in any form, was the enemy of civilization. Even in his 80s, Ricardo still spent time at the test benches, quietly analysing pressure traces and noting temperature drops with the same curiosity he'd had as a student at Cambridge. Visitors found it hard to tell where his retirement began, because for him, inquiry was simply a way of living. Sir Harry Ricardo died in 1974, aged 89. He left behind no monuments, only motion, engines, textbooks, and a philosophy of precision that shaped the modern world. His work bridged the age of steam, petrol, and jet propulsion, proving that progress depends not on chance, but on measurement. He once wrote, "The engineer's task is not to invent energy, but to prevent its waste." That idea still drives every efficient engine built today, a quiet echo of the man who turned combustion into science and gave the 20th century its rhythm of power.